Hi everyone, let us talk for this track before the closing message. Hi Roland, how you doing
Hi,
today? I hope you enjoy the conference so far.
absolutely wonderful conference.
Thanks, and we are ready to watch your talk about Bayesian computation. And okay, I leave the stage. Thanks a lot.
Thank you, thank you. So it's wonderful to participate at this magnificent conference. Specific thanks to Marco and Alessandro for putting together and organizing this conference with very insightful and interesting talks. And of course, huge thanks to all the speakers uh, for um, for giving absolutely fantastic talks, and I'm very happy to participate as well. So I'm Roland. Yes, I work as a researcher in Moscow Institute of Physics and Technology at the Nuclear Physics Methods Lab, and I also have my own company called Grinis, which develops software, specifically simulation software and data analytics software. And recently, we started to build some open source libraries, and one of them, very niche, yet a very early stage project, is NOAA, which is a Bayesian computation algorithms library. And we use C++, and we build it on top of LibTorch. In fact, our initial plan was to, and still the aim, was to build something where we could run Bayesian inference in systems such as one you will find in algorithmic trading. Typically, for example, you would have, say, for those applications, you will have some in-memory database like KDB, and you want to sort of run your numerical application as close as possible to data, but yet in a concurrent way. So writing it in C++ was a very important point for us. Yet you want to leverage all the heavy linear algebra and automatic differentiation and all sorts of other numerical computational libraries written over the years, and obviously written in C, Fortran, or sometimes even run things on CUDA, on GPU using CUDA. So you being avoiding overhead from FFI, or even worse, any sort of process communication or copying data was important for this type of application because of the data coming in. You have also similar situations when you want to integrate some computations and analytics into, say, a rendering engine or a games engine, like in OpenGL or Vulkan. Obviously, you don't want to kind of copy around the data or run it in some other stack. You want to be close. But very recently, also, I got given my collaboration with the Nuclear Physics Methods Lab, we developed simulations for particle physics. And so simulations for particle physics, here is also an interesting story, because a lot of stack written by physicists is happening on C++. You have libraries like Giant developed by CERN, and you have also libraries like Root, also C++, which is used to store and analyze data. And basically, you need to write something which can reuse some of that C++ code, and then also being called from that C++ code. So somehow, and yet you don't want to kind of, because it's a simulation still, you don't want to add some overhead for things you don't want to see. At the same time, you want to obviously to keep a balance between research and production. So there are obviously many interesting computational libraries in C++. That I will mention in a minute, but LibTorch somehow was a game changer for me. I should actually tell you a bit that I'm not initially a C++ developer. My career started as a Scala developer and on Morgan Stanley, and then I worked in different fintech startups using Python most of the time. But when I start to tackle the problems I just mentioned, C++ was somewhat a game changer, and the LibTorch or the LibTorch C++ API actually offered the tools required to make some of those projects happen. Let me mention some of the great packages available also for Bayesian computation. Those include PyMC3. I think it's built on top of Theano, or they're trying to move to TensorFlow. It's a probabilistic programming package. You have BoTorch, Bayesian optimization, written over PyTorch. All of this is in Python. And LibTorch was actually the kicking point for this implementation in C++. It's a recent algorithm in Hamiltonian Monte Carlo, which deals specifically with high-dimensional sampling from high-dimensional distributions, and which have sometimes high curvature. And in that sense, a lot of other PyTorch, so that was developed by Adam Cobb and his collaborators, and many other researchers in machine learning and data science. They put up those algorithms in Python, in PyTorch. And actually, because PyTorch has such a great integration and is so close to Python, it's easier to kind of keep up with the research. For example, I should mention in C++ the Stan package, which is absolutely fantastic, groundbreaking work on Bayesian computation. But it just can't keep with the latest research. So they're stuck at 2014, the NOTS algorithm, and they haven't. And if you want to implement something new, then you're sort of stuck a bit. Plus, of course, PyTorch is not just Stan is of course probabilistic programming, but PyTorch is also focused. PyTorch is not focused only to that. It's a general programming computational platform. In particular, you can also use, of course, you can use deep learning, and that was the whole point of my talk. And the example I want to show you is how to use it in deep learning. Of course, running those type of things in Stan is more complicated. At the same time, PyTorch also offers you the 10 libraries, the AutoGrad library, which enables you to do linear algebra and run automatic differentiation for whatever applications you need, and leverage this. And of course, the integration with deep learning is very important. So the Torch script engine, so that you can most of the deep learning models are in any case are sort of pre-trained if you want to do particularly interesting things, and then you need to be able to upload them into your C++ thing. And then in that sense, actually, I would like to point you to Matthias and Eric. Wonderful talk on AI for Prod, where they touched upon some of those issues as well, using ONNX. And yeah, I should have mentioned also Julia. Julia has very powerful Bayesian computation libraries, and it's quite a lot used also by the scientifics. But Julia is Julia. You kind of, if you write in Julia, you're stuck within Julia. If you want to move somewhere else and reuse that code, then welcome FFI, or welcome whatever RPC or whatever you can come up with to reuse that code somewhere else. But yeah, so in that sense, C++ had is a bit notorious in the way it's not necessarily easy to prototype, but I think LibTorch offered us a way to actually have both research and production at a very good balance. So you get the speed, and you also get the prototyping utilities that you need. And saying about prototyping, actually, I'm reading here a Jupyter Python notebook. Basically, I've built a bunch of C++ utilities that I'm gonna simply open to Python and run. And it's particularly nice for prototyping because Torch has a very nice integration with Python given PyTorch. Actually, Torch comes bundled with PyBind, so don't get your own one. Just include Torch extensions, and then write. And you can, if that was our main purpose, to write a library which is just header only and just relies on standard C++ 17 library to make it look a bit like what I'm used in Scala or Python, and also I have a Lightning at Thunderstorm, and at the same time you write full C++ code. There is no, I'm not trying to play any games with you. As you can see here, I'm releasing the GIL, so everything is really happening in C++. I'm just to play around. It's nice to do it in Python. You can have access to this notebook on the NOAA repository, GitHub repository. So yeah, let me just import Torch. I obviously run already this notebook to make sure that everything works. See, this is just for some plotting. Actually, you can run this notebook also on Colab. Just on Colab, because I use C++17, I didn't bother to kind of being careful about older versions. I make sure that you have GCC 8 installed on Colab, and then you will be able to run all that stuff on Colab as well. So here we go. I'm just going to get those extensions. Obviously, we're going to look at the implementations in a few minutes, but I'm just going to build them. You can specify C++17, no worries. LibTorch is actually C++14 library, but there is no worries about using C++17 constructs. So here we go. We have loaded all C++ stuff. So let me just generate. Let's move to the meat of the presentation, and let me explain why. To start with, why Bayesian approaches sometimes prefer to the frequentist one. And I'm talking deep learning. Typically, people will take a video or an image to show, but I'm going to go very simple because I want to show you a very concrete problem with frequentist approach to deep learning. That meaning the overfitting nature, or how you call it, overfitting culture that goes with deep learning nowadays. And it's difficult to show this on images, but it's very easy to show it on simple data sets. So look, I'm just gonna generate that and plot it. So it's just if you want to look at the C++ code, it's as close as you want to come to Python. So for someone who is more computational or more quant as I am, it's very nice and use. And obviously, as I have listened to Sandor's talk, I'm now desperate to put the const qualifier everywhere I can. But obviously, yeah, in this case, we are going to do something very simple. We're just going to draw a sinus and then generate some random points around this curve and pretend that this is our training data set. And what we want is to model this curve, basically. To model this curve, we're going to define in Python, we are going to define just a three-layer deep learning model. So it has a 10 by 10 layer inside. So actually, if you can compute, there are 141 parameters actually involved in this very simple but small network. If you think that at some point I'm going to run Monte Carlo Markov chain, you should start to worry, because this is a really huge set. Most of the Monte Carlo Markov chain algorithms start to crack at 3 dimensions. Yet we're going to do it. So I'm just gonna script this neural network, and I'm gonna train it. I'm gonna show you in C++, of course. I'm gonna show you the C++ training in one moment. Let me print the result of this training loop. So you see overfitting at its best. So the curve, this is the final optimal solution, absolutely goes through every single exactly. I think the training error is very close to 0. Yet it's clear, that if your evaluation data will come here, you will have a massive error. And in some sense, when you work with people, say you work with a trading desk, you work with a trader, you have a model, and it outputs, it predicts something, then the trader also doesn't want also necessarily to know, okay, how you model it, but he wants to understand also the risk of, if we wiggle a little bit the data, what is going to happen. And the problem is that if you wiggle all sorts of things, you from this optimal solution, you absolutely have no idea what's going on actually near the solution. If you started somewhere further away, or how sure are we about that we are really close close to the point. So you don't really you find it very hard to estimate the risk involved with overfitting. And so here the nice C++ training loop. So we just load this net model. Obviously, people like Matty and Eric, they have it a bit more complicated for them because they use on NX, and it's more complicated to train. But if you just stick with PyTorch, going from Python to C++ is super easy. You define a loss function, you define an optimizer, and then you pass in the parameters to your optimizer. You define the step, and then you run 250 loops, and then the result, you just return it up to Python. And because I use only STL and the PyTorch tensor type, I don't need to fiddle around. Python will understand this as a list of tensors, no problem at all. So when I get this here, it's very easy to plot. And I should say that it's it's an important point for us quants. Being able to actually run this stuff and play around with the code we build as we build it in C++ is very important, because for prototyping, it's the best way to move forward. So in some sense, this is very close to actually just write Python and prototype with it, because we need to plot things, we need to change some parameters. So in that sense, it's a very positive experience. But yet you are this loop is fully within C++, so you can run it or do whatever you want in the usual C++ way. There is no Python involved on. Like, for example, I should remind you that, for example, if you work with KDB in finance, and Q has an interpretability with Python, but actually it calls a Python interpreter within Q. So it's a much more sort of, you have to be careful about that. And obviously all the multi-threading or anything is lost. You can't use the callbacks in Q or anything like that. But here it's just it's not just the way that you define a model in Python, then you train it. It's also that you can develop your algorithm. But going back to the philosophy of computing things, so the frequencies approach is really about, you ask me, so what are the parameters for my deep learning model that give me the highest probability of observing the training data, the red points I obtain? And obviously, with such a point, you are just running an optimization, and then you find some solution which at least near the solution, everything seems to lead to higher probability, but you don't really understand is this the best, or what you can do that, or what are the risks that actually you found the best solution to your problem. But in practice, in practitioners and scientists as well, actually what they prefer to ask is, given that I have observed that data and maybe that I have already some idea about what the parameters of the net are, can you give me what values of the parameters of the deep learning model are actually more likely to happen? So it's really you're trying to really have a prior vision about what the distribution of the parameters are, and then you get some data, and then you use that data to get the distribution for those parameters. And of course you have this Bayes rule, and I'm gonna just sample. We're gonna discuss in a minute how to run the sampler, but so here I generated 7,000 samples, and I'm gonna just run. Oops, this is thunderstorm. Run some of them. I will take half of the samples, and I'm gonna plot for you. So this is just Python plotting code. So because it's so many samples, it just takes a little bit. So here you actually see somewhat a bit of a better picture, because here you have the solution, which is you have a distribution for the parameters. So it's a distribution over 141 dimensions. So it's a huge distribution, and I computed mean. The mean is exactly this yellow line. But then I have all the samples around it, and it gives me a good idea about, okay, if I wiggle if I wiggle a little bit around my optimal solution, the samples, then I can then this is how the curve behaves. And then now if someone comes to you, tell how probable is how much risk of is there with this, for example, training data, or that one, you can say, oh, okay, well, this one is a bit of an outlier, or this one, but this one we're pretty sure that we're heading toward. And as new data actually comes in, then you can compare. You have a whole probability distribution for your parameters. Moreover, you can actually simply for every now turn to the actual probability distribution of the predictions of the model. So you just take the prediction, take the mean, and sorry, I'm running a bit of Python, but in that sense, you see how good is it to program in to have this interportability between C++ and Python, so that you can do some of that thing here. And you can actually plot now. You can actually plot the curves, the mean, and one standard deviation away from that mean. And so now you have a whole probability distribution, and you control better the idea of what overfitting and what is not overfitting in your situation. Okay, so hopefully that sort of have convinced you about why Bayesian approach is more insightful, more useful for maybe scientists and business people to kind of digest the analytics your team as a software developers, machine learning engineer, and quant data scientist, you provide to them. So you can formulate quantitatively what are the risks involved with your model, and also to digest better new data as it comes in, to understand whether it fits into this probability distribution, or you need to actually update your parameters, and how stable is your model with respect to those parameters. So all of those questions can be answered from those probability distributions. But okay, so how did we manage to sample from such a huge probability distribution? Well, we use Hamiltonian Monte Carlo. So that goes back to physicists for many years already. That has been used. Essentially, they compared to stochastic gradient, Hamiltonian Monte Carlo lift the whole space. So normally, if this is the distribution of your parameters, then we're gonna lift. So actually, I should give credit for this picture to Colin Carroll, who used it in his talk for PyMC3. But basically, the idea is that for the algorithm, we lift the parameters and we sample from what's called a phase space. So we are actually simulating something called Hamiltonian dynamics, for those of you who recall some of their physics class. But the idea is essentially that we're sort of solving a classical mechanics problem where the potential is your log probability density, and basically we'll spend more time where the log probability is higher during this is physics, than where it's lower, and this idea actually get a very efficient scheme for you to sample from such huge distributions. Obviously, so to start with, obviously in C++, so how do I construct this sampling scheme? Well, obviously, so first of all, I need to construct the log probability associated with this with a neural network. So essentially, as I remind you, as we have generated the data here, what we essentially assume is that we have some baseline, and given the training data, given the training points, I assume that the output from the true value of the model is normal. So essentially, the Y train, so this variable is Y train is distributed normally around the value of the neural network at that point. So we have a normal distribution, and essentially, when you actually use the loss as a MSE loss, you're actually implicitly assuming that. So when I said here that you're training your data set through by maximizing log likelihood, this is exactly what you're doing, because this loss function is exactly the negative log likelihood, so hence the minimization. But if you but in practice you want to maximize the log likelihood. But in our case, so we in our library we provide you with a function which enables you to build this log likelihood. So you give me the net, the model. So the model variance is a variance of the normal distribution around for the white train. White train around the value of the deep learning. So the smaller the model variance, the more sure you are about your model that the data will be close. The bigger the model variance, the less you expect a bigger error from the data you see than than what you can actually provide with your model. And the same happens with the now prior parameters, because the prior parameters you need now to have a view of what the probability distribution before you've seen the data. Typically, it's just the normal distribution with mean 0 or some random mean. But here again, you have a variance, and so if you give a large, and you should typically give a large variance for the parameters, because you're not quite sure about what they are, so that when you see the data and you compute the base rule, then you actually get a more focused distribution for the parameters, and you can answer this question. Now, obviously now from there, once you have constructed your log probability distribution, you have to set up the configuration. Now Hamiltonian Monte Carlo works in an interesting way. So there are two configurations you have to set. The most important ones is that actually compared to stochastic gradient, when you just evolve the optimizer step by step and get a new point, Hamiltonian Monte Carlo provides you with whole trajectories. So actually, when it lifted to this phase space, it's gonna start with the parameter you provided, generate a momentum, and then evolve solving the Hamiltonian dynamics and return to you a whole trajectory back. And it's up to you in Hamiltonian Monte Carlo, when do you stop this trajectory and how do you sample from that trajectory? So there are various ways to do that. But essentially, in your loop, compared to the stochastic gradient, you will be getting chunks of new parameters that you will have to decide how to deal with, and you just set up a max flow. So for how long do you evolve those steps? And essentially, each time you lift from the parameter space to the phase space, you will end up in different energy levels, and you explore different trajectories. And ultimately, of course, if you do it randomly, you will explore the whole probability distribution. So we come now to the most important part: is we create. This is this is related to the Euclidean dynamics. So this is related to the optimizer. So we create this dynamics. So you need to give me an identity. So you have to give me a metric, basically. So this is sort of the covariance. And actually, to deal with probabilities of high curvature and high dimensions, you actually want this to be the Hessian of the distribution. And this we implemented also in our library. But because I'm sort of running out of time, I'm going to skip a bit from this idea. But the idea is that you can configure the whole sampler in a way that you will generate those trajectories. Essentially, because we use a C++17, we just set up everything in terms of lambda functions. So you will have to provide me with a lambda function which tells you at what point you want me to stop. Typically, it's a Metropolis Hastings step, meaning that when you see that the log probability start to drop, then you stop the trajectory. And you also provide me with a bunch of log probability distributions regarding how do you resample from this trajectory. And also, we are implementing some stuff where sometimes the trajectory comes back to itself, and in that case, you want to also stop the trajectory. But ultimately, you want to sample and get as many trajectories as possible, and ultimately you will obtain this picture after you run this C++ code. Obviously, the notebook will be available for you to rerun on Colab. So just to mention what are the problems and what are maybe less positives. The problem is that when I define the log probability density, then I've used the whole training data set, essentially, the whole training data set. And as you know, in deep learning, you load the training data set in batches. And it sort of doesn't, there are algorithms now, there is current research about how to improve that, but this is somewhat of a problem. So in some sense, Bayesian computation still works for somewhat smaller problems than you can actually address with stochastic gradient. So for example, like transfer problems. So essentially, you typically want to have a good idea about what your parameters of the model are that you've obtained from a stochastic gradient descent, and then you want to sort of as you obtain new data, see how those parameters get changed through the Bayesian step. In that sense, Bayesian computation in practice is best used for online learning. So when you have data coming in and you want to kind of look at, or new data coming in, and you want to kind of understand how your model reacts. And in that sense, for example, to finish up my talk, for example, I will generate, I will mutate, say, the last data. So for example, we got some update at this point wasn't quite there, but actually was up. And so now I can generate a few trajectories, but not that actually this time I sort of lowered down the variance for my, because I'm sort of more sure about what the parameters are. So if I generate this thing, and again, I rerun the loop of the sampling, then given this new point, I'm obtaining a picture when now, compared to stochastic gradient, my prior parameters were the optimal parameters to obtain with stochastic gradient, and I wanted to sort of sample around them. But as I get to this new point, what essentially you can see that the model is saying, aha, hold on, actually your point, this point, given the shape of the distribution, is somewhat higher than you expect. So maybe all of the points you had before, they were a bit lower. And so you obviously now the model is telling you that there's much more risk involved, uncertainty, I would say, with a model than you say. And this is what people in practice, in trading or in science, like specifically, is because you can come back to them and say, okay, we have new data, and we can quantify the uncertainty involved with this new data. And so really, Bayesian computation is here for streaming analytics and online learning, rather than trying to train BERT or ResNet on top of it. So that's basically my talk. And let me take some question. Actually, I'm sorry, I forgot to look at the Q&A side, but yeah, let's take the good question by Silong Ling. How old is Marco?
Yes, here I am. Yeah. Thanks for the talk. I wasn't expecting that you were finishing so fast. So let me add this. This is the question. So how well does Bayes' method scale with the complexity of deep learning model in terms of sampling speed and convergence? Is it feasible to use Bayes in SOTA models with billions of parameters? So two questions, actually.
So for Hamiltonian Monte Carlo, it's definitely possible to use it with several hundred of thousands parameters. The only problem is your training data set, it has to fit in the memory. The problem is that if the training data set doesn't fit into the memory, then you can't then you have to sort of, the stochastic Hamiltonian gradient is not quite stable yet as of the research. But the dimension is not necessarily a problem. One problem comes around is if you want to use not the Euclidean Hamiltonian Monte Carlo, which has been known for years and years and that I'm using here, but you want to run the Riemannian Hamiltonian Monte Carlo, where this metric that I use and that I assume the identity in that case is locally computed from the Hessian of the, then of course a Hessian of 140 by 140 tensor is now a huge matrix, and obviously here the computational part comes. But as I said, if you those methods are particularly nice for online learning because you don't need to, in that case, instead of actually running stochastic gradient and trying to overfit and data mine this new point and chase data, you're actually telling me, no, hold on a second, I know we've computed those parameters before. We have a good idea about what those parameters are, and then small data comes in, and then you then you can define, of course, the log probability density. But now with the whole information about what the parameters were before are actually in the log probability density function, and then you can update your point of view of what this model is, of what this of what the model is given that new data. But yeah, it of course, stochastic gradient descent will be a much faster way to train a model because it just gives you less information.
Thanks. We have time for one last question, if there is any. So let's wait for a few moments, and then I think we can get the last coffee of the day, and then in 10 minutes we can have the closing message in this track. So, okay, I think we don't have any more questions, I think. So thanks a lot, Roland, for the great session. I think we'll personally catch up with also Mattia and Eric later, maybe in the next few days, because we are all interested in these topics. They are all topic of our job. So let's catch up later about this.
Absolutely, with huge pleasure, and thank you very much for everyone for listening and having an interest. And of course, I will probably send to you the link to the Colab. To the notebook, so that people can rerun it on Colab if they want.
Yes, we are going to publish it. Yes, definitely, in the description of the video.
And also, I should say the library is very. We just kicked off, so we were sort of developing and testing it more and more, little by little. So yeah, it's not necessarily stable yet, but at the same time, we implement some very cool stuff from cutting edge research.
Great, awesome. Thanks a lot again, Roland. For all the other people attending, just 8 minutes, and so take the last coffee of the day and closing message in 8 minutes in this track. Thanks. Cheers. See you later.
Bye.